Today our topic is analysis of algorithm. An algorithm is a step-by-step instruction to solve a problem. When we create a program, we have to think the logic of that program and we have to write that logic step by step in a simple English-like language. So when we write a program, it should be readable or understandable by compiler. But algorithm is readable or understandable by human. The analysis of an algorithm is a major task in computer science. To solve any problem, it happens that there are a number of algorithms. So we have to analyze which one is better. The goal of analysis of algorithm is to compare algorithms mainly in terms of running time, but also in terms of other factors like memory, efforts, etc. The time and space used by the algorithm are the two main measures for the efficiency of the algorithm. The time is measured by counting the number of key operations, that is in sorting and searching algorithm, the number of comparisons. The space is measured by counting the memory needed by the algorithm. There are three possible cases. One is worst case, second one is average case, and third one is best case. Take one example, then this will be more clear for you. In linear search, we access each element of an array one by one sequentially and see whether it is desired element or not. So by linear search, we want to search a particular element. Say I want to search 34, and in this array 34 is in 0th index, that is in first position. So how many number of comparisons is needed? It is only one. So number is 34. I want to search 34 in this array by linear search, and I search it sequentially and I get our required element at the first position. So number of comparisons is 1. So this is the best case because the element present in the first position. So total number of comparison is 1. Take another example. Say I want to search 76. First compare, is this 76? No. Then check the next item, is this 76? No. In this way, I have to check one by one item sequentially and finally I get 76. So this is average case. Here we assume that item appears in the array and that it is equally likely to occur position in the array. Take example for worst case. In this case, if I want to search that particular element which is present at the last position of the array or not present at all, means say I want to search 66. So I have to search from the first element of the array and I check each element sequentially and finally I get 66 at the last position of the array. So I have to traverse the whole array to see which one is our desired element. Or if I want to search say 97, is 97 is present here? No. So you have to search the whole array and finally you conclude that 97 is not present in this array. So this is the case for worst case. See, so in case of worst case, if the element is the last one or not present at all. In a nutshell, we can say that in worst case, this represents the input set that allows an algorithm to perform most slowly. Worst case analysis requires that we identify the input values that cause an algorithm to do the most work. In the worst case analysis, we calculate upper bound on running time of an algorithm. We must know the case that causes maximum number of operations to be executed. For a searching algorithm, the worst case is one where the value is in the last place or is not in the list. Next, average case. In average case analysis, we take all possible inputs and calculate computing time for all of the inputs, sum all the calculated values and divide the sum by total number of inputs. This represents the input set that allows an algorithm to deliver an average performance. Next, best case. This represents the input set that allows an algorithm to perform most quickly and take shortest time to execute. It causes the algorithm to do the least amount of work. In the best case analysis, we calculate lower bound on running time of an algorithm. We must know the case that causes minimum number of operations to be executed. For a searching algorithm, the best would be if the value we are searching for is found in the first location that the search algorithm checks. So, it is told that to find the complexity of an algorithm, we will find the worst case. Rate of growth of big O notation. When we analyze an algorithm, we just ignore some cases like in which hardware this program will run, in which environment this program will run, etc. We just test the logic, that is which logic is better in same environment. The time of algorithm depends on the number of input data. As for example, if we search largest value among 10 numbers, then 100 numbers, then 1000 numbers, then time will vary depending on the inputs, though the logic is same. Rate of growth of Biggo notation. If n is the size of the data, then the complexity of an algorithm increases as n increases. It is usually the rate of increase of function fn that we want to examine. This is usually done by comparing fn with some standard functions such as log2 base n log n square, n cube, 2 to the power n. The functions are listed in the order of their rate of growth. The logarithm function log2 base n grows most slowly. The exponential function 2 to the power n grows most rapidly and logarithm function grows most slowly. Next, definition of big O notation. Given two functions fn and gn, we say that fn is on the order of gn, that is fn equals to ogn if there exist two positive integers a and b such that fn less than equals to a into gn for all n greater than equals to b. So this is the definition. I am taking one example, then this will be more clear for you. Now see the examples. Prove that for each of the following pairs of functions, fn is the order of gn. Now see the discussion. Our first example is fn equal to n square and gn equal to n cube. I have to show fn is on the order of gn. That is, what is the value of fn? It is n square. What is the value of gn? It is n cube. So n square is equals to order of n cube. So I have to prove n square is on the order of n cube. From the definition, I can write n square less than equals to a n cube, where a is any positive integer. Our first positive integer is positive 1. So value of a may be 1, 2, 3, but first positive integer is 1. So in place of a, I write 1. So n square less than equals to 1 n cube for all n greater than equals to b. From both sides, I cancel out n square and I get for all n greater than equals to 1. So if a equals to 1 and b equals to 1, then I can say that n square is on the order of n cube. Our next example is I have to prove n square plus 100n is order of n square. So from the definition again I take n square plus 100n less than equals to a n square. Now if I take a equals to 1, then n square plus 100n less than equals to 1 into n square. So from both sides I can cancel out n square. Then 100n less than equals to 0. So n less than equals to 0. But this is not the condition. So I have to take this one. N square plus 100n less than equals to value of a is 2. So n square plus 100n less than equal to 2 into n square. So I can say that 100n less than equals to n square. So if a equals to 2, b less than equals to 100. So if a equals to 2, b less than equals to 100, then I can say that n square plus 100n is order of n square. Our next example is I have to prove n square plus 100n less than equals to O n cube. So by the definition again I am taking n square plus 100n less than equals to a n cube, where a is any positive number. I am taking our first positive number 1. And from this equation, I get, by applying Sridharacharya formula, I get the value n as 11. So if a equals to 1 and b less than equals to 11, then I can say that n square plus 100n less than equal to order of n cube. Now some theorem. First, transitive property. If Fn is on the order of Gn and Gn is on the order of Hn, then Fn is on the order of Hn. Theorem number 2. If Fn is on the order of Hn and also Gn is on the order of Hn, then Fn plus Gn is on the order of Hn and Fn minus Gn is on the order of Hn. And if Fn is equals to C0 plus C1 into n, C2 into n square, in this way finally Cn into n to the power n, then Fn is order of n to the power k, or Fn is order of n to the power k plus j, any greater order. Take some examples. See, for the first equation, Fn equal to 7n square plus 100n. What is the maximum power of n? It is n square. So what is the order of this function? It is order of n square. For this equation, what is the maximum power of n? It is n cube. So what is the order of this function? It is order of n cube. According to the order, there are three types of functions. One is logarithmic order, that is fn equals to order of log n. Another is exponential order, that is fn equals to order of d to the power n. And third one is polynomial order, that is fn equals to order of n to the power k. Now see more examples. Our first example is proof that c into n equals to order of n. So from the definition of the order, we can say that c into n less than equals to a into n. Now in place of a, if I write c, then c into n less than equals to c into n for all n greater than equals to 1. So if the value of a equals to c and b equals to 1, these conditions satisfied. Our next example is proof that c into n equals to order of n to the power k. From the definition, we can write c into n less than equals to a into n to the power k. If we write in place of a c, then c into n less than equals to c into n to the power k for all n greater than equals to 1. So 1 less than equals to n to the power k minus 1, that is for all n greater than equals to 1, that is b equals to 1. So if a equals to c and b equals to 1, we can say that c into n is equals to order of n to the power k. Our next example is proof that n to the power k is of order n to the power k plus j. Now from the definition, I write n to the power k less than equals to a into n to the power k plus j. If the value of a equals to 1, then n to the power k less than equals to 1 into n to the power k plus j. So 1 less than equals to n to the power j for all n greater than equals to 1. So if a equals to 1 and b equals to 1, we can say that n to the power k is of order n to the power k plus j. Logarithmic function. Let us suppose two logarithmic function log m base n and log k base n. We have to prove that log m base n is the order of log k base n. So what is log m base n? It is log k base n into log m base k. So log m base n, if log m base k is a, then we can write in this way log m base n is equals to a into log k base n. So from the definition, we can write log m base n is of order of log k base n, where k equals to 1, which shows that any logarithmic function is on the order of any other logarithmic function. So we can just write order of log n. Find out the complexity of the following program. This is a program for Fibonacci series. I have to calculate the complexity of this program. Okay, so from line 1 to 19, these lines are executed only one time. So the count is 1 for these lines. For line 20, this for loop will executed n minus 1 times. And the last time when we compare with this condition and condition becomes false, then also this line will be calculated. So total number of execution for this line, line number 20, it is n. And within this for loop from line 21 to 26, these lines are within this for loop. These lines are executed n minus 1 times. And line 27, this line is executed only one time. So after calculation, I get this result. What is the maximum power of n? It is 1. So this result is order of n. So these are your homework. Choose the correct option and answer me in the comment section what is the correct option. I am waiting for your reply. This is your theory assignment from complexity and Biggo notation chapter. For getting more and more updates, please like, share and subscribe my channel. That's all for today. Thank you.